So as said already, we are going to have this tutorial about next generation intrabody technologies for biomedical sensor network. And in the first part, I will take care of presenting the technique that we use in our lab, coupling technology for body area network, while in the second part, my colleague Laura Galluccio will talk about the ultrasound technology. So for my presentation, I will first outline the general architecture of body and intrabody area network that usually up to now still use radio frequency technology, both in wearable and implantable setting, but we are proposing some alternative technology because of some limitation of the radio frequency. In particular, I will focus on the coupling technology, galvanic and capacitive coupling. Finally, I will show you the contribution that we are working on in the standard XC Smart Band and some application of our research work. In general, you can imagine to have a subject where you can consider several types of device, both wearable and implantable, able to acquire several types of physiological data, such as blood pressure, ECG, EEG, EMG. So all these type of physiological data may be collected in a data aggregator with different type of technology in the body area network, and then once collected, they can be sent remotely to a medical doctor for remote monitoring. As you can imagine, this way, more personalized medicine can be applicable, and also a more proactive delivery of appropriate actions. In general, when designing this type of device, the design criteria are mainly focusing on the size. Of course, we would like to have the device as much as small as possible, and the power consumption. As you know, the power consumption is a stringent requirement in wireless sensor network, and even more in this type of biomedical sensor network, not only because of the energy constraint, but also because you need to avoid tissue heating of the subject. Also, it's also important the security and reliability of data, because of course you need to trust the transmission of this important physiological data, while the data rate is less stringent, because in general this type of biomedical data are low frequency data. This is a general communication scheme. You can see here, for example, a sensor that is implanted inside the body, here in the muscle tissue, and is able to acquire biological data. This device can either send the data to an external device that is placed on the skin, or directly send an instruction to an actuator, for example, for drug delivery. In case of the data are sent outside in a device on the skin, for example, this is possible for continuous medical monitoring. And when talking about the communication of the devices inside the body, several types of technology may be applied. As I said before, radio frequency is still the standard, mainly for the wearable scenario, but some has been considered also for the implantable setting. But at this frequency, the electromagnetic frequency, have limited penetration tissue, which turn out in high signal absorption, which may turn off in heating of the tissue that, of course, we would like to avoid, because that's a security for the person. So we need alternative communication technology for the scenario in intrabody communication. As we outline here, these are the main techniques that are proposed as alternative to radio frequency. So ultrasound, which is based on mechanical vibration, and other types of electromagnetic methods. There are some at high frequency, microwave, millimeter wave, terahertz, and optical, and others to low frequency, which are basically inductive, capacitive, and galvanic coupling. At high frequency, of course, also this type of technology suffer the attenuation, but you can imagine that they may be used for other type of purposes. For example, optical solution can be useful not to send data on a long transmission range, while, for example, since the wavelength is really low, they have the possibility to interact in nanoscale with small cell. So you can imagine, for example, the interaction at neuron level. The stimulation of the neurons may be more precise compared to what has been done up to now. Some word about the other. Microwave technology, there are some works that are thinking to the FAT as a waveguide. The FAT is more a dielectric tissue, while the other two layers that are the muscle and the skin can be thought as more conductive. Hence, we have this effect of waveguide. So, because of that, it's possible to reach longer distance when the transmitter and receiver device are placed in this fat tissue. At millimeter waves and even higher terahertz, it has been seen that the attenuation is very high, but as said before, the purpose of this type of technology at higher frequency may be different. When talking about the low frequency, we have the ultrasound that is based on the water content of the human body, and the working principle is based on acoustic communication, while the other three, inductive, capacitive, and galvanic, are still electromagnetic wave. The inductive coupling is based on the high magnetic permeability of the tissue, and can be considered as the gold standard for powering the implant. The capacitive and galvanic coupling have some common points. Basically, they both use electrodes as transmitter and receiver, but in a different configuration. As you can see here in the figure, for example, capacitive coupling has just one of the two electrodes of the transmitter. One is attached to the skin, while the other, the ground electrode, remains floating. And the same configuration is done at the receiver. On the contrary, galvanic coupling has both electrodes at the transmitter and the receiver that are attached to the body. And because of this different configuration, also the physical principle is different. In the first case of the capacitive coupling is based on electric field, while in the other case of galvanic coupling is based on weak electrical current that are flowing in the body. This is a table that summarizes quickly the feature of all this type of technology, and each of them has its own benefit and drawbacks. For example, if we think about tissue safety and security, ultrasound and galvanic coupling are the best one, because the working principle make the waves to be confined inside the body. While if we want high data rate, higher frequency technology, of course, show better result. In this tutorial, we will talk just at one link layer, but in general, if we like for other type of network, in case we consider several type of device, also the other issue of the protocol stack, MAC layer, network layer, have to be considered. Regarding the testbed, we have already some testbed. Here are summarized the one related to nervous system application. And you can see on the left, the ultrasound testbed that is able to reach sub-millimeter size. And in this case, this testbed was able to both power the implant and transmit the data. In the middle, you see high electromagnetic frequency. On the top is the testbed related to the fast waveguide that I mentioned before, while in the bottom are the high frequency terahertz devices. And finally, the low electromagnetic frequency technology that are basically the testbed for capacitive and galvanic coupling to send neural data, also imagery, for example, or electromyography data. In this table are summarized the value of this testbed. As you see, for example, the power column, all these technology are able to work at low power, and they have been applied to different type of application related to recording, monitoring, and also stimulation of the nervous system. Now I'm moving to the galvanic coupling technology that is the technology I work on. So basically the working principle, you have two electrodes in the transmitter that represent your transmitter and two electrodes in the receiver. As you see on the right, there is one main circuit that is between the electrode of the transmitter, and the main primary current is flowing in this circuit. Anyhow, there are some secondary weak current, the orange one, that flow in other tissue. And this current may be detected by other two electrodes represented by the receiver. In the figure is depicted the placement on the skin, so the wearable case, and also the current are shown just one on the skin, but you have to imagine that also other current are flowing in the other tissue. This technology is able to work with low value of the current, 0.5 milliampere, and is able to reach tens of centimeters. You may employ both commercial electrodes, like the one depicted in the figure, or even smaller size electron. And as you see here, the energy consumed by the galvanic coupling is much lower than, for example, the ZigBee, that is one of the standard of the radio frequency. And this is the frequency range that goes usually from 1 kHz to 100 MHz. The main feature of the galvanic coupling technology is that the signal, since there are current, the signal is restricted inside the body, hence is interference-free and secure because there is no propagation outside. As you can see here, for example, the magnetic field, when you go to low frequency, as in the first case, 100 kHz, the field is almost confined inside the body, while going up in the frequency, then the field spread out outside the body. In general, there are two main approaches to model the channel of galvanic coupling. On the right, you see the simulation model. So you have to think to finite element model, where the electric field and magnetic field are simulated in 3D, and there are specific software for that. While on the left, you see the other approach, the equivalent circuit model, that is based or on the two-port model. Basically, there is just the potential difference at the transmitter and the receiver, and you define the transfer function and treat the channel as a black box. But there is also the lumped element model, where you consider all the internal voltage and current of your model. That's because, in general, the tissue may be represented as an imperfect dielectric, which means that has both the dielectric and the conductivity property. Indeed, for example, as in the figure, the membrane has this capacitance effect at low frequency, which means that low frequency currents are not able to pass the membrane, while high frequency current can pass through the membrane. We took for the channel characterization a different approach. We took it from the telecommunication studies. Indeed, instead of simulation and circuit model, our approach is based on the channel impulse response, based on real experimental measurement. In particular, we consider these 4 configurations, which means both capacitive and galvanic coupling in wearable and implantable configuration. As you can see on the top, we have the wearable setting. The difference between capacitive and galvanic coupling is that while in capacitive coupling, only one of the 2 electrodes of the transmitter is attached to the skin, and the other electrode, the ground electrode, remains floating. In the galvanic coupling, all the 2 electrodes, both the transmitter and receiver, are attached to the screen. Up to now, the wearable capacitive coupling is the most used one, while in the plantable setting is the galvanic coupling, the figure D. Basically, the electrode of the galvanic are all implanted inside the tissue. But recently has been proposed a new version of the capacitive coupling, the implantable version, where the electrodes are all implanted, but the ground electrode is isolated with a dielectric isolation layer, the red one that you see in the picture. And this ensures a similar configuration of the floating ground electrode from the wearable setting, while we are considering the implanted setting. Regarding the channel impulse response model, we use a correlative channel sounder, which basically consider the received signal, Y signal, given as usual by the convolution between the transmitted X signal and the impulse response H. When you correlate each side of this equation by the transmitted signal X, you get the cross correlation. The first term is the cross correlation between the transmitted and received signal, while on the other side you see the autocorrelation of the transmitted signal and the impulse response. If the autocorrelation of the transmitted signal approach a delta function, basically if you just make the cross correlation between the received and the known transmitted signal, you are able to get the channel impulse response. And that's what we have done. We use pseudo-random noise sequence as transmitted signal because they have this good cross-correlation property to have the autocorrelation that can be approximated with a delta function. So our cross-correlation between the received and the known transmitted one gives us the impulse response. And this is the block, the experimental test, but used to get the channel impulse response. So we use 2 PC and their sound card. Why the sound card? Because they work in a subset of the frequency range of the galvanic coupling. So we generate in a MATLAB program the transmitter, this PN sequence, that were passed through the sound card, where a jack, line-out jack is connected, a wire is connected with 2 electrodes, which are the transmitter of the galvanic technology. These 2 electrodes are attached to the tissue. As you see in the figure, there is a real leg, and the opposite similar configuration is done at the receiver. Here we apply just a convolution match filter to get the channel impulse response. And these were the real configuration setting where we consider both small electrode size in implanted scenario, ex vivo chicken tissue, or wearable electrode with 1 centimeter diameter. Since we know from previous work from simulation that both galvanic coupling and capacitive coupling have a non-frequency selective behavior, we wanted to test it experimentally. And we verify that we have this type of frequency flat channel If we see here in time domain the cross-correlation function, you see that there is just one peak, a bit broader, but just one. So in case of multipath channel, we would have seen more than one peak, which says that in this type of technology, we have just one channel, simple channel. And this is very important because it means that our transmission chain may be simplified. And this is in line with the need of this intra-body area network to have simple and low power devices. The same feature can be seen also in frequency domain with the channel frequency response that is somehow in the frequency range considered, can be considered flat. And always the capacitive coupling is showing higher gain compared to galvanic coupling, both in wearable and implantable setting. One thing to say is that this less investigated implanted capacitive coupling is very promising. Why? On one side, because as you see in the figures, we have higher channel gain, and which means that we are able to reach longer transmission distance, but also because they are in line with the requirement of high miniaturization. Why? If you remember at the beginning of the section, you see here the configuration that the capacitive coupling has this red isolation layer that allow the two electrodes of the transmitter and the semi-active receiver to be as close as possible, which means improve the miniaturization, and this without changing the setting of this type of configuration. The same does not apply to the galvanic coupling. In galvanic coupling, if you put closer the two transmitter electrodes, this translates in lower distance between the transmitter and the receiver because the main path of the current is close in the first circuit of the transmitter, and then there are lower, weaker secondary current that goes towards the receiver. So this is a great result of this new implantable capacitive technology. Now we are also starting to study what up at higher frequency, because up to now we were working in up to 100 of kilohertz, but now we are moving up to megahertz with similar consideration. After the channel model, some words about the experimental testbed. This is similar to the testbed that I show you for the channel model. So there is just two personal computers, one for the transmitter, the other for the receiver, which are connected through the jack line, the audio jack line from the transmitter to the tissue, the real tissue, through electrodes, and the same on the other side. So it's a very simple configuration. And this is the parameter setting. We have implemented the full transmitter chain. These are the usual block of a transmitter for wireless transmission that can be also implemented in this type of technology. And these are the block of the receiver, which basically can be divided in signal recording and digital down conversion and burst detection and symbol time estimation. Without going in the details, we were able to estimate the transmitted signal. Here is represented in the frequency domain before the modulation, so in this band, and after the demodulation. But the bit error rate at the beginning was not really good, not as expected. And this was due to the frequency correction that was missing, which means the frequency offset between the local oscillator of the transmitter and the receiver that was making the bit error rate not very good. And we solved this problem, achieving very good bit error rate result. And here, since they were very low, we put the signal to noise ratio. comparing with different type of modulation scheme. After the implementation of the testbed, we sent real electromyography data. So the scenario that was considered was this one of the nerve compression. So imagine to have a muscle that is not receiving the signal from the nerve because there is a compression of the nerve. So our idea was that we could use the signal received from close healthy muscle and use that to trigger the suffering muscle. So the idea is to take the received signal, the electromyography signal from the healthy muscle and transmit via galvanic coupling to the suffering muscle. And then here, an amplifier and an actuator will use these to trigger and create the movement of the suffering muscle. We have acquired the electromyography data, and then we have transmitted them both in wearable and implantable configuration. On the right, you see the figure of the reconstructed data while changing the transmission power. And also in this case, the signal-to-noise ratio were very good. We were able to reach a signal-to-noise ratio around 10 dB, which is equivalent to a bit error rate in the order of 10 elevated to -6, that is very good considering that we have no error correction code. And finally, something about our contribution to the ETSI Smartband standard. Regarding this type of coupling technology, there is something going on also in IEEE in the standard A02.15.6, but they are considering just one type of configuration and the frequency is centered at 21st megahertz. In our case, we are considering several types of configuration with both capacitive and galvanic coupling in different wearable and implantable settings. So we opened just a few weeks ago the new work item specifically for this coupling technology. Which are the applications of this intra-body communication in both wearable and implantable? As I said before, I show you the case of the nerve compression that we extended later in the nerve lesion. As you see in this figure, we imagine a scenario where the signal cannot reach the final muscle because of the injury. So the signal can be acquired before the injury, for example, with some cuff electrode that acts like rings around the nerve, and then the signal is processed and can be transmitted via intra-body technology, for example, with galvanic coupling or ultrasound technology on the other side after the injury, where another electrode, this ring cuff electrode, can be used as actuator to trigger the muscle with the signal, with this signal that was sent via intra-body. We went further with this application and we have a project related to facial palsy. And the concept is similar. You have to imagine, for example, that with unilateral facial palsy, there may have a lesion on one side on the main trunk of the nerve. But since the face is making symmetrical movement, we thought that it will be possible to use the healthy size where the signal arrives to the branches of the nerves to collect them here and transfer via intra-body communication to the other side where the signal is not reaching the final branches nerve. And now the biology colleagues are working on putting this cuff electron on real rats and are acquiring the signal. After this step, we will start the processing of the data and then the transmission of the data. Also, we have used the galvanic coupling channel so the specific data of the channel to extract a secret key for a secure communication system. This is another type of application that we have. While going on the wearable setting, we are developing a device, a wearable device to acquire an electrocardiography signal with a bracelet. So the idea is to acquire the signal and detect if there are anomalies so that we can autonomously send an alarm to the alert system. And this will be unique because up to now the device that are wearable usually need the involvement of the person, but in case of particularly problem, you can imagine that the person cannot be reactive. Last application is this one related to the acquisition of physiological data for astronauts. So in this scenario, we are thinking more to wearable device. We are thinking to electrocardiography, PPG, electromyography, specifically focused for the case of microgravity, like in space. And this funding will be also transferred to other type of cases, such as a person on the bed in the hospital, because they suffer similar problem. So this will be useful also for this type of disease, such as, for example, osteoporosis and other diseases. Okay, these are the main references that I use in my presentation, and now I leave the floor to Laura Galluccio for the ultrasound technology.
Good afternoon, everybody. In this second part of my presentation, I will start talking about ultrasonic communications for body area network. This is basically, let's say, the counterpart of this unconventional communication discussion, where in this first part we talked about coupling techniques, and now we are going to consider a different type of waves. So I will quickly try to motivate why going to consider ultrasonic waves, what are the physical layer design aspects that need to be considered, and then I will present you some experimental activities that we have carried out at the University of Catania. And so I will shed some light on evolutions of the use of ultrasonic waves inside the human body by way of considering wave-guided propagation. And last but not least, we will see how the use of digital twins can empower the ultrasonic technologies. So as we said very quickly, the scenario that we are going to address is this one where we specifically need to have both intra-body communication for all those sensors that collect data inside the human body, and then external communication to a gateway that can be either a smartphone or a smartwatch or whatever towards the internet. And the focus of this talk will be mostly on this intra-body part. We have already discussed that the radio frequency waves are very, very limited in performance when we think about using them in human body. So the employment of unconventional technologies such as the ultrasonic waves becomes very, very successful because it allows to increase a lot the tissue penetration, which is one of the main limitations of radio frequency waves. It's not so, let's say, annoying in terms of signal absorption, and is also very secure because in order to eavesdrop the communication which involve our personal health data, you should be, let's say, in close contact with the environment where the propagation is happening. So eavesdropping is impossible, basically. So when we talk about ultrasonic waves or ultrasounds, we are referring to frequencies that are above the human hearing capabilities, so higher than 20 kilohertz. This type of waves exhibit very good communication performances in all those media where there is a huge water content. The human body is perfect from this perspective because it's composed for more than 70% of water. They are not electromagnetic waves because we are now talking about mechanical vibrations. So they are mechanical waves where the energy propagates as a wave and travels from particle to particle through the medium. And also there are some consolidated technologies that can be employed for transduction, the most famous of which is piezoelectric transduction, but also ceramic transducers are pretty much utilized. Although we will see that there are more, let's say, innovative technologies, especially when we go to the nanosize. We already discussed about the pros and cons that these unconventional technologies exhibit. What is worth to highlight is that in case of ultrasonic waves, we are able to increase the transmission data rates, so they could be suitable for the case where, for example, we want to transmit, let's say, gastro-duodenoscopies or similar type of video data. They are very safe for the reasons that we discussed quickly before and that we are going to detail more in a while, and then also very, very secure. So the ultrasonic waves are indeed used in medicine since 1960s approximately because they are safe waves. They present no health risks. All of us know that, for example, they are used for fetal screening and they are also very efficient and effective. In fact, we remember that in underwater scenarios, so a bit different application, but which with some commonalities with intra-body communications because the medium is purely water. Acoustic waves are employed and they are the most widespread methodology also from a commercial point of view. And also the World Health Organization recognized that the diagnostic ultrasounds is a safe, effective, and highly flexible imaging modality. And it's very useful also in terms of trading off cost effectiveness and fast use. There are, as I mentioned before, some health considerations, however, that should be taken into account because as in many other different contexts, there is the need to reduce eating because every time we apply energy to internal tissues, part of the energy is absorbed by the tissues and can be converted into heat and can lead to this overeating of the tissues. However, we know that no lethal effects are met when the temperature remains lower than 41 Celsius degrees, and also we know that this is a function also of the time interval during which these episodes could happen. In order to reduce this risk of incurring into eating, it is important to try to reduce the wave intensity because the wave intensity is the one that leads to this possibly overeating of tissues. So duty cycling can be an answer to this problem. Here in this right side of the slide, I reported some information that come from the FDA recommendations on the maximum ultrasound intensities in terms of milliwatts over square centimeters that are recommended by the US FDA for various applications. And you can see that the intensity depends also on the tissues. For example, ophthalmic tissues are those where the lower intensity values should be supported. Another concern that needs to be considered when using ultrasonic waves is the possibility to reduce the risk of incurring cavitation. Cavitation basically means that due to this compression and rarefaction because of these mechanical waves, there is the possibility to incur into bubble formation, and these bubbles keep on having these unstable sides, and thus in principle they could lead to a violent collapse. They can lead to kinetic energy effects and due to bubble implosion. So in order to reduce the risk to incur into this type of issues, the exposure should be limited. And again, here I've reported some FDA recommendations in this sense. So now that we have tried to understand why choosing ultrasonic waves and what could be the risks to take into account when we design a system that employs this technology, I'm going to discuss some physical layer elements that are needed to cope with when we use transmission of a very, let's say, unconventional type. So ultrasonic communications are, as I told you, mechanical pressure waves. So they can be characterized in terms of the frequency, the amplitude, pressure, the propagation speed, and as I said, the intensity. There is a way to describe the propagation of these ultrasonic waves inside tissues, and this can be done in terms of acoustic pressure, which is, let's say, varies as a function of the location, so in terms of the coordinates x, y, and z, and also as a function of time. And this behavior can be described by way of the wave equation. Here we also see the dependency on this parameter v, which takes into account, that is the speed of sound in the medium, and which takes into account the angular frequency and the wave number. Also, one of the key elements is the parameter alpha that represents the attenuation of the wave that propagates inside the medium. And this is related through the Stokes law to some parameters like the angular frequency, the density rho, the viscosity, and so on. When considering thus the propagation of ultrasonic waves in human tissues, we see that the pressure decreases as a function of the distance at which we propagate, and so an initial pressure P0 decreases exponentially as a function of this alpha parameter, which, as you can see, depends on A and B, that are parameters tightly related to the specific tissue. So in this table, we report, for example, A and B in case of blood, heart, kidney, liver at different frequencies. And in the plot on the left side, we show accordingly how the attenuation varies as a function of the operating frequency for different distances. So basically, the higher is the distance, so for example, 10 centimeters, that we want to penetrate, the higher will be the attenuation. And this needs to be coped when we do some design. In this slide, we also reported some experimental data that we obtained by characterizing the attenuation as a function of the frequency for a human body phantom, that is this one reported here, that is a block of ballistic gel that exhibits the same features of the human body tissues, embedded with organic tissues like chicken bone. And these are the two situations. This case when the tissue was when the phantom was without the organic tissues, and this case when there was this organic tissue. Please note that the attenuation depends, as we said, on the size of the block. So the farther we go, the higher the attenuation will be. And also we see that there is always a minimum for these attenuation curves that is around 3.5 megahertz, which is also a range of frequencies that we have chosen to design our system. Now, just few words to say what are the kind of equivalents of the antennas in this case of ultrasonic communications. In this case, we have some transducers, so devices that transform electrical signals into vibrational waves. For example, in case of a piezoelectric transducer like this one that I have reported here, we have always an active element, this one, for example, in case of a piezo. This is the black rectangle here. Then there is this baking, which is used to absorb the energy radiated on the back face. And then we have a wear plate that protects the transducer. However, when we want to go to lower sizes, and so we go, for example, to nano sizes, because we are thinking about, for example, implantable devices, there are alternative technologies that are more suitable to these very low size. For example, the PMUTs that use MEMS for piezo actuation, or the CMUT that use capacitive micro-machined ultrasonic transducers. Or also opto-ultrasonic transducers that employ this optoacoustic effect, so we can generate high-frequency acoustic waves by irradiating a medium with an optical wave, or also the graphene. And so single-layer graphene, which can be used for, again, acoustic wave generation when an electric signal of sound frequency is applied to a single layer graphene, and so there is a Joule effect in proximity of the surface area, and the periodic vibration generate these sound waves. When we consider these transducers, we should also focus on the radiation pattern of the transducer. Why? Because depending on the application, it would be typically required, especially when we talk about intra-body communications, to be very focused in the transmission of the beam so as not to impact unneeded areas of the body. So there is somehow a trade-off that needs to be considered when we want to design a transducer between its sides in terms of the diameter, as we can see here, and the beam width. In particular, this is the relationship that puts everything together. So basically, the directivity, which in intra-body applications should be very, very high, should be traced with also the frequency and the diameter. So for example, in case of short range communication, so from micrometers to millimeters, high frequency are useful, while in case of long range, so on distances larger than centimeters, much lower frequencies are required. It is clear that in a feasible and realistic scenario, devices, implanted devices could not be so close to require short range of communication, but they are expected to be much farther away. That's why the frequency to be used cannot be so high, and that's why this goes into the direction of the minimum attenuation around 3.5 megahertz that we identified before. So on the one hand, there is the need to decrease the attenuation, which implies using low frequency and low directivity. On the other hand, small size means small diameters, low directivity, and thus finding a trade-off between these different options is needed. Also inside the human body, due to the very small organs, the very small particles, reflections and scattering are met, which can be described either using the Snell law for acoustics or using some equivalent models like the Nagakami distributions. Here I have reported some experimental results that we have developed and obtained for the characterization of the channel impulse response, similarly to what was illustrated before by Anna for the case of the coupling technologies. In case of ultrasonic waves, here we have assumed that the model, the CIR, can be described by way of a tapped delay line model, where we have different components, each having its own gain and its own delay. We experienced that indeed these components are visible, as we can see here, due to the multipath. Which makes these type of environments very challenging, and this multipath is met also when there is no organic tissues embedded, even if the problem becomes less critical. And in this case, we also represented the three main components, so the direct wave, the reflected wave, and the lateral wave that propagates around the phantom, and we report the CDF for the mean excess delay and the CDF or the root mean square of the delay spread. Now I'd like to show you some pictures and a very short video where I illustrate the testbed that has been developed at University of Catania that employs these ultrasonic waves, and a few hints on the ongoing projects in this direction. This is the plot that represents the structure of our testbed. We have two USRP and 210 that are software radio platforms controlled by way of a new radio software. In this case, we have 4 transducers. They are ultrasonic transducers. They work in the range between 1 and 6 megahertz for the reasons that I discussed. We have some switches that are used to share the software-defined radio lines. And we were able also to test the case of a multi-op transmission with these 3 ops from T1 to T2, T2 to T3, T3 to T4. Here I also reported some details about the hardware that we use. This activity has been started together in collaboration with Northeastern University, and we also have a couple of international patents on this technology. This is a picture of our system. These are the power amplifiers. These are the switches. This is one of the 2 USRP, and this is the other one. And these are signal generators. This is the phantom. In this case, you can see a leg of a chicken. So it was one of our initial experiments with much larger tissues. Here we see instead the case where we transmit an ECG across this phantom of the human body by considering a single op. And I also have this short video where you can see that the transmission goes on until the 2 are in contact. When we move the receiver, the transmission stops, and then when we connect it again, the transmission starts again. And we did this also for the gastroduodenoscopy video, and also in multi-op, where there was this other equipment put here so that the number of ops was increased up to 2. This is the project that my colleague already mentioned that we have ongoing. What is very, very interesting from our perspective is that we want to implement this kind of mirroring from the healthy side of the face, where the transmission of the signals across the nerves can work properly, to the paralyzed side. And in this sense, we are considering the possibility to go either in a complementary way by considering coupling techniques and ultrasounds, or also using the 2 technologies in parallel and testing their efficiency. Also because the presence of a lot of chronic bones could lead to some additional complexities in terms of propagation of the signal from one side to the other side of the face. Clearly, we cannot test these due to ethics issues on human bodies, so we are going to do this on mouses, and the vibristal experiments have already started. Other couple of hints about evolutions of this activity on the use of ultrasonic waves. So why not moving from a diffusive perspective, which is the one that we already discussed, to a wave-guided approach? In this case, the idea is to use blood vessels as wave guides bytes, where we can increase the communication range, which in case of diffusive communications on a single hop could go around 14 centimeters. This is an example of what happens when we simulate this in the COMSOL multiphysics. And instead, when we try to waveguide the propagation by using the total reflection similarly to what is done on optical fibers, this is the equivalent representation in COMSOL multiphysics. We can see that the communication range moves now to 35 or even 40 centimeters by using the reflection in the Fraunhofer zone, which is equivalent to the far field. Last but not least, why don't we use digital twins that are so common now in 6G networks together with ultrasonic waves? Why? Because we are talking of two complementary approaches, one working at the physical level, so ultrasounds, the other working on a higher level. So in this case, the idea is to develop real-time medical monitoring systems that can continuously track the human health parameters and can adjust at runtime the transmission parameters based on the feedback coming from the digital twins. Why? By using some learning methodologies, specifically a multi-armed bandit methodology, which allows to optimize, to enable this adaptive tuning of low-level parameters. Specifically, the parameters that we can tune will be modulation schemes, payload length, transmission power levels, and so on. So the idea is to have, this is my forearm, these are two transducers, so still we have done this only in one hop. And so we have a transmitter and a receiver at the physical layer with the two USRP controlled by the two laptops, and at the virtual layer we have the two digital twins that talk to each other and adjust based on the execution of a MAB the parameters of the communication. This is what we can do. For example, this is my forearm, which is equivalently represented through this phantom having also the organic tissues with the skin, with the muscle, the bone, and so on. And in this case, for example, we can change the modulation schemes between a BPSK, GFSK, GMSK. We can tune the size of the payload, the length in which we split all the text file that is sent based on the conditions of the medium. This is just an example of the new radio code and modules to tune the sender and the receiver. The multi-armed bandit, just to have an idea of what is done, employs different actions to maximize a long-term reward based on the actions that are chosen. In this case, the actions are a combination, each action is a combination of a modulation value, a carrier frequency, the gain, and the packet length. There are different methodologies to implement this multi-armed bandit problem. One of those, the simplest one and most common, is the epsilon greedy algorithm, where the actions are selected in such a way that what is considered the best action based on the rewards that were in the past is chosen with probability 1 minus epsilon, otherwise the others are chosen with probability epsilon. This is the reward that we have based on the intent that we want to achieve, if it's purely throughput or packet error rate or a combination of both. And these are just a couple of results which show you what is happening thanks to this methodology by using two different MAB algorithms, the poor epsilon greedy or an epsilon greedy that is memoryless, so it doesn't take into account the previous history, and based on different intents. If the intent is poorly throughput, and so we only weight throughput, or if it's a poorly packet error rate, and so minimization clearly of the packet error rate, or if we consider 50% throughput output and 50% packet error rate, both in case of low noise, so a very safe environment, or another more busy environment where we add artificially a high level of noise. And we see that the system follows very well in both conditions, and the two algorithms perform quite well, especially the simplest case, which is the epsilon greedy. This simply reports a few references about the activities that we have done together with my colleague Anna Vizziello, and also only here at University of Catania and in cooperation with Northeastern University. Just to say that we have also applied for the possibility to open another work item in the ETSI ban smart group about the use of ultrasonic waves, again as a low-level unconventional technology in parallel with what is done for coupling techniques. And this is pending approval. Thanks a lot.